of Euler identity. That is the equation e in exponent I pi plus 1 is equal with 0. So first of all, let's see e in x, how we can be in the power series form. So we have e in x. So let me write here e in x is equal with 1 plus x in over 1 factorial plus x squared over 2 factorial plus x cubic over 3 factorial, and it goes on. So this pattern continues until infinity, 5 factorial. So this can continue. But now we have the expression in this form. We have, for example, e in ix, because we want to look to resemble this equation here, e in exponent I pi. And it's going to happen this way. 1 plus ix over 1 factorial plus I square x square over 2 factorial plus I cubic x cubic over 3 factorial. And this equation continues this pattern as I mentioned previously, over 4 factorial plus I in 5 x in exponent 5 factorial, and goes forever. But now if we are rearranging a little bit of this equation here, we can write e in exponent ix is equal to 1 plus I in exponent I times x over 1 factorial. Then here we have I squared, but I squared is a minus 1. So we can write a minus 1 times x squared is a x squared over 2 factorial. And here is a I3 is a minus I. So this is a minus I x cubic over 3 factorial. And this I4 is 1. 1 times x4 is a x4. We can write a plus a x4 over 4 factorial. And here is a plus I in a 5 is a I4 times I1. I4 is 1. 1 times I is a I. So here we can write I x in a 5 over 5 factorial. And let me go in the I6. I6 is going to be, for example, I4 times I1. I4 is 1 times I square. I square is a minus 1. So this one, we can write this one. So just let me erase this one because it's not very good. So this one can be, we can write in the form, because I in a 6 is a minus 1. So it's a minus x in a 6 divided by 6 factorial, and this pattern continues. So what we can do here now, we can write e in exponent ix is equal to the 1 plus, so just let me rearrange here. And because I have here 1, let me write those x squared, x4, x6 that do not contain I, the I imaginary, pure imaginary part I. So just the real part, we can write 1, and this one, just let me change the sign here because it's not a very good. The sign is a minus because it's a minus x squared over 2 factorial, minus x squared over 2 factorial, and here is a plus. You see here this is a plus x4 over 4 factorial. So this one here I can take, and this one here. So it's a plus x4 over 4 factorial. And is a minus 6, x in a 6 over 6 factorial. And what we can do next, you see here in all of this part is a I imaginary part, so let me factor I. Here is a plus I in an exponent, I'm sorry, I times x over 1 factorial is just x. I can write this as just x. And here is minus x cubic over 3 factorial, minus x cubic over 3 factorial. And what do I have here? I have a plus x in a 5 over 5 factorial. As you see here, odd numbers are in this side and even exponents are in this side. And x in a 4. So, and this continues. This continues. Okay, this can continue, but always it contains x in exponent, even exponents, and does not contain the pure imaginary number I. but this one is odd exponents and contain the imaginary part. This is x in a 5 over a 5 factorial, and this continues. And what do we have now? We have this situation. But if we look, for example, this power series, we can write as a cosine x. And this one we can write sine x. And in ix, we can write as a cosine x plus I sine x. And now, since we have a e in a I exponent pi, so this was in a I. Okay, so this one we can write e in a I pi can be equal with the cosine pi plus I sine pi. And let me go a little bit further. And now, instead of e in a pi, we can substitute this equation here with this expression cosine pi plus I sine pi plus 1 is equal with 0. Cosine pi is a minus 1. You can check in a calculator. And sine pi is 0. Plus I times 0 plus 1 is equal with 0. And here is a minus 1 plus 1 is equal with 0. So we already proved. So this Euler identity is equal with 0. We already proved. And here I'm going to stop.